So far in this course, we've seen different modes of operation of transmission electron microscopy, understood the imaging theory, and covered important aspects of high resolution electron microscopy, looking in TEM mode and in STEM mode. While we introduced the electron lenses and also started looking at different imaging modes, there was one important point that we were always mentioning, that the quality of the electromagnetic lenses is quite poor, and because of the lens aberrations, you are severely limited in the resolution that you can achieve in an electron microscope. In today's lecture, I'll be discussing on a very important topic called aberration correction in transmission electron microscopy. This has actually been a breakthrough in the field of transmission electron microscopy. The invention of aberration corrector by Harald Rosa, Maximilian Heider, and Knut Urban, and simultaneously by Andrei Krivanek and Nicholas Delby. It actually revolutionized the area of transmission electron microscopy by breaking the 1 angstrom barrier. Initially, people were thinking that to achieve very high resolution, you actually need to have very high voltage, and there are the side effects of having high voltage electron microscopes where the specimen damage is quite prominent. In this lecture, we'll see the parallels between aberrations in optical lenses and electromagnetic lenses, what has been the challenge and the so-called Scherzer theorem, and how to break the symmetry of electromagnetic lenses and construct aberration correctors, and understand basic functionality of aberration correctors. The sources that I have referred to in this particular lecture are primarily these papers that I've shown here. These are some fantastic resources and there's a lot of information here. I tried to simplify most of the content from all of these. In particular, the company that manufactures the aberration correctors called CEOS Germany, this has immense number of resources. In particular, there is this page called Workshop Contributions where slides from all these workshop lectures and also the foundations and the theory of electron microscopy and various important terms are described in a very well manner. In fact, you would have the manuals along with most of the aberration corrected microscopes. Please try to go through them. There's a lot that you can learn from them. And more importantly, as a student, I had the opportunity to attend a workshop conducted by Professor Christian Koch in Manchester, and I've looked up, I was lucky to find some of these slides on his website, and I'd like to acknowledge that as a student, learning the image simulation theory or attending the workshop kind of gave me better clarity in understanding aberration correction, and I also kind of referred to the pre-congress workshop slides, in fact, to also help develop the flow in this particular lecture. So hopefully these resources and quite a few more resources like the ones available on the microscope manufacturer websites would actually be helpful for you to understand some of the topics that are on the frontier of the field of electron microscopy. So let us start by looking at aberrations. The core principle in aberration correction is you should understand that aberration correction is not really a technological trick, but it is controlled engineering of electron wave front. So here is where I start drawing the parallels. I'll introduce the concept of wavefront error by taking examples from optical lenses and the classical Seidel aberrations. Then there is something called as the Zernicke polynomials, based on which you describe aberration as a polynomial function. And we'll also look at the electron optical constraints or the Scherzer theorem. And then, of course, resolution limit is something that we've discussed in initial lectures on high resolution electron microscopy. But primarily what you should understand is by losing out on the higher frequencies in the Fourier space, you're actually cutting out the resolution that is mainly due to the aberrations, and this is the link that we'll establish as we go through. And the concept of multipole correctors, which is more on the engineering aspects of how the aberration correctors are built and how it actually functions. So, when you look at the situation of an ideal lens, when you take a simple glass lens, you would expect that any rays going through the lens, they would all converge at a single point. This is in the most ideal situation. But in reality, these would not really coincide at a point. If I look at the realistic situation, it appears something like this, where the rays which are like this, perpendicular to the principal axis, you call the rays indicated with M as the meridional rays, and these are the sagittal rays. And because there are several lens aberrations, the rays that are actually traveling in this direction are not coinciding at a single point, and these rays are also not coinciding at a single point, and because of this you are actually creating a sort of a disk of confusion. When you start learning the classical ray optics, what you actually look at is you try to fit in a sphere in this particular location here, or you can think of this as a spheroid kind of a structure, and or an ellipsoid kind of a structure rather, and the diameter of this is related to what is called as spherical aberration. So, in an ideal situation, you have very small angles, you have almost the paraxial approximation, the rays are close to the axis, and it is in perfect imaging condition that all the rays meet at one point. In reality, the rays have a finite angle, they pass at a finite distance. So, this distance here, you can measure it, and in reality they actually miss the ideal focus. So, when you look at the definition of aberration, you actually call it as the deviation from an ideal Gaussian imaging. So, this is what you have practically any lenses, because of several imperfections, they would not certainly coincide at a single point. The rays that travel through the lens would definitely not coincide at a single point. So, by measuring how much these deviations in the waves are, you can kind of understand that you can represent this dimension or the aberration that you have through some kind of an expansion in terms of a polynomial, and we'll look at how you understand this in the upcoming slides. So, if you want to understand and quantify aberration, in classical optics we have something called as the Fermat's principle. So, what you understand is, this is from the foundations that we actually look at lenses and the light interaction with lenses in a pure geometrical way. Light follows a straight path, the optical path is also stationary, and the path length does not change under small variations. So, this is what your Fermat principle states. So, if I look at the deviation in the path length in an ideal situation, you would have it as more or less 0. So, an ideal optical system produces a perfect wavefront, but we saw in the previous slide that this is far from the reality. So, in an ideal situation, all the waves or the rays of light will arrive in phase at a single point. So, it can be focal point, or if you are looking at a point on the image plane, they all coincide at a single point, and in reality this is not the case. So, the stationary optical path is not perfectly satisfied, you always have some path deviation, and you can look at aberration in terms of what is called as phase error. So, the optical path, it actually varies across the wavefront, and rays are no longer coinciding at a single point, and they are not arriving with an identical phase. So, the image then, as a consequence of this, becomes distorted, and that is what we see leads to lens aberrations. So when I define aberration, it is actually deviation of the wave phase from the ideal wavefront. And the understanding of this from geometric optics to wave optics, you can draw a comparison that light travels as straight lines, but in wave optics we describe light with the equation looking at it like a complex number, and you have the phase there, and the errors that you have in the imaging can be described through ray deviations, whereas when you look at it in terms of the wave optics, you describe it as phase errors. And this is largely geometry based and wavefront based. So essentially, if I want to correct the aberrations, whether it is in an optical lens or even in an electromagnetic lens, if I can engineer the wavefront and ensure that all the rays are more or less coinciding and arriving in phase at the point of where I am recording the image or the diffraction pattern. In fact, at the back focal plane of an objective lens, if all the waves that I have interacted with a specimen are coinciding at more or less the same point, you've more or less corrected for the aberration. So the whole idea of aberration correction is engineering of the wavefront. So if I want to describe the errors that I have in the wavefront, because we already introduced the term aberration as a deviation in the wavefront, you can describe the wavefront errors in terms of some kind of a polynomial, and we call this as the wave aberration function. You can describe it in terms of the angle with respect to the optical path and the deviation with a radial component from the optical path. So alpha is the aperture angle, it is the direction inside the lens, and r is described as the field coordinate, it is the position in the image or the object plane. So any complicated wavefront can now be built in terms of a polynomial. So the coefficients that you have here and the polynomial with varying powers can describe any kind of, or more or less most of the wavefronts. So you can build with simple mathematical terms the wavefront to describe an aberration, but it is not really ideal because the terms here are not independent, and it is hard to relate to physical aberrations, and there is a poor numerical stability as well. And the solution to this is a concept that was introduced by a very famous Dutch physicist in the year 1934 through a concept called Zernike circle polynomials. So with this, you are now describing the wavefronts in terms of circular polynomials, and with this you can get a better description of any kind of a wavefront. So let's understand what these Zernike circular polynomials are. So if you look at the idea, I just told you that these were introduced by Fritz Zernike. In fact, he was awarded the Nobel Prize for the development of phase contrast microscopy. So with the Zernike polynomials, you can actually have a consolidated mathematical way to describe three-dimensional wavefront deviations. So the polynomial in fact represents a specific wavefront shape, and by changing, like even in the polynomial you have similar coefficients like this in terms of alpha and r, and by changing the coefficients and the powers of these, you can fit in with individual wavefront shapes. You can more or less think of various complex aberrations. So to simplify this or to draw parallels, you can think of decomposing a wavefront shape to summation of polynomials, or through the Zernike polynomials is analogous to looking at a Fourier series, but it is designed for circular lenses. So the mechanism here in these Zernike polynomials is you write the wavefront as sum of polynomials, and each polynomial corresponds to some aberration mode. it could be defocus, it could be two-fold astigmatism, and so on, and we will see what these are. So, the coefficients here determine the strength of each of these aberrations. So, the accuracy in these Zernike polynomials is much better, and you can add enough number of these terms to describe any kind of a wavefront in a more precise manner. So, if I look at the wavefront error and in terms of the Zernike polynomials, initially if I look at simple polynomials, we had the terms alpha and r, and if you recollect from the lens, when it was not coinciding at a single point, the error that we had can be fit in with the help of some kind of a polynomial function in terms of alpha and r, and if I look at the lowest terms of these polynomials, I have either the alpha cube, r alpha square, r square alpha, and r cube. So, if I look at the some dimension of these, it is a third order kind of an error, and these are the basic non-ideal terms which cause aberrations for any lenses, and these are called the Seidel aberrations. So, these are actually spherical aberration, the coma, astigmatism, field curvature, and distortion. What we will do now is, you have probably already seen what aberrations are and how they look for, how they appear like in optical systems. Perhaps you might have seen them in your high school text, but let me just show you an example with some ray diagrams on how the classical Seidel aberrations actually look like. So, the classical Seidel aberrations are, of course, spherical aberration. If you look at the ray path here, they are all not coinciding, and there is kind of a blur or a distortion that is created at the back focal plane of the lens. Then you have the off-axial coma. Now, usually when you look at all the ray optics, you only think of unidimensional propagation, and you are often not looking at the sagittal component of the lens. What this coma actually tells you is, when I am not looking at only one dimensional propagation, but looking at it in the 3 dimensions, when I have this off-axial source here, it actually can not coincide at a point, and it can result in kind of a blurring on the image plane here. So, this deviation, if I move from here to here, it can change from a shape like this to a shape like this in this direction. So, this kind of distortion where the radial component cannot be neglected is actually called as coma. And then you have astigmatism, which is essentially non-intersection at a single point, that is how we described. And then you have the curvature of the field. So, suppose you have a lens where the propagating wavefront does not have a uniform surface, and there is some kind of a curvature that is created. The objects that are slightly far away from the optic axis, where you are sort of deviating slightly away from the paraxial approximation, you see some kind of a blurriness. This is commonly observed in optical microscopes with very small working distances, and in the field of optical microscopy, this is corrected with different mechanisms by either using combination lenses, or there are several other methods as well. But this blurring is actually visualization of the curvature of the field. And then we have distortion. So, even in distortion you have barreling or pin cushion or S-shaped distortion. Because of some kind of errors in the surface of the lens while you are manufacturing, you can lead to these kind of distortions where an object which is supposed to appear nearly square, it tends to deviate into a shape like this. These are commonly observed with poor quality lenses. Now, using the Zernica polynomials, if we simulate the propagating wave front, which results in these kind of aberrations, at the image plane or at the back focal plane, you can think of visualizing these aberrations with help of some kind of wave fronts which appear like this. So, in a simple diagram, it appears like this, but in reality, the effect of these aberrations or the distortions can appear somewhat like this. So, spherical aberration leads to a distortion like this. Of course, you have it on the other side also. I am only looking at the projection upwards, and then coma gives you this kind of smearing effect of the beam, and then astigmatism, field curvature and distortion. This is how the wave fronts would look like. So, to summarize this, in spherical aberration, the rays at different distances from the optic axis focus at different points. In coma, the off axis point sources produce these comet-like tails. In astigmatism, the rays in different meridians focus at different distances. And in field curvature, you have the image plane which is not really flat, you have some kind of a curvature, and it is somewhat sort of opposite of spherical aberration that you see here. And in general distortion, there is variation in magnification or lack of focus across the field. These are the common errors that you actually see with optical lenses, and the field of optical microscopy and the formation of lenses is almost over 300 years old, and there is enough experience that people have actually found ways to deal with these kind of problems that you have in optical lenses. Now, if you have these kind of problems within electromagnetic lenses, it only makes the system lot more complicated. Let us now start drawing a comparison between the aberrations in optical systems versus the electromagnetic lenses. So, for optical systems, you have sort of aspherical lenses. You can fix them with you can fix the spherical aberration either by using doublets. You can have somewhat kind of a convex and a concave lens together. There are various ways in which you can have multi-element systems, or you can have some kind of an aperture stop adjustment with various corrections. You can actually do aberration correction for optical system. Like I was mentioning, the field is quite mature and very old, that people have actually learned how to deal with or minimize the optical aberrations quite successfully. There are more advances, the adaptive optics with dynamic real-time correction, digital correction, and also something called as correction collars. If anyone is interested in this, you can look at the website of Zeiss. They have nice descriptions on these, on how the correction collars are actually made. So, you have some kind of microscope cover glass correction. So, it is sort of well known and reasonably mature field, and it is corrected and dealt with in a reasonably good way. But when it comes to electromagnetic lenses, there are some problems. If you look at the electromagnetic lens, the main parallel that you can think of is the optical analogy of an electromagnetic lens is always a convex lens, because if you recollect the discussion we had on electromagnetic lenses, it looks like a coil or a solenoid in which you apply an electric current and it produces a magnetic field which is along the axis of the electromagnetic lens, and in this situation the charged particle or the electron beam that actually goes along the optic axis would only tend to converge. And when you have these kind of symmetric electromagnetic lenses, you can describe the magnetic field and the electric field of these lenses through the electrostatic potential and also the magnetic potential of the lenses. And based on this, Otto Scherzer, I mean, they've been working on this from as early as 1930s, but in around 1960s, I think, it was proposed that especially circular electromagnetic lenses, you cannot get rid of either spherical or chromatic aberration because you have a rotational symmetry of the fields. So, the lens fields, they inevitably show spherical and chromatic aberrations under the following conditions. So, you have rotational symmetry and you have static electromagnetic field and there is an absence of space charges. So, because of this, you can severely degrade the performance of an electron microscope, and that is one of the reasons why when there were not advanced electromagnetic lenses and stable electric and feedback loops and the digitization was not there, the aberrations were more prominent and it was difficult to go past 1 or 1.1 angstrom resolution in the older generation high voltage microscopes as well. If you look at the initial early days, even with field emission microscopes, with microscopes that were before 1995 or so, the best resolution you could achieve was perhaps 1.8 or 1.6 angstrom, and it was a real challenge to break the 1 angstrom barrier. So, largely the limitation of the electromagnetic lenses and the lens aberrations severely limited the resolution you could achieve in the electron microscopes, and with rotationally symmetric lenses you actually cannot correct for these spherical and chromatic aberrations. That is because the fields that are there in these electromagnetic lenses should actually satisfy the Laplace equation for potential, and the potential also cannot have any arbitrary curvature, and as a result you would have some kind of positive spherical aberration and also positive chromatic aberration. So, basically electromagnetic lenses are fundamentally constrained by the physics of how these lenses are designed and how it operates. Bear in mind these are circular lenses, but it is not such a problem for glass lenses. So, people were able to correct for aberrations in glass lenses versus electromagnetic lenses. So, to summarize this, if you look at the spherical aberration in optical lenses, it is reducible. Even the chromatic aberration, you can have achromatic coatings or surfaces which help you reduce this, and the symmetry of optical lenses also, by using combinations of constructions, it is flexible. But in round electron lenses, you always have a positive CS, and with the instabilities in the systems that you have, with the kind of sources you use, and also the issues that you have with the achromicity with the electron source as well, chromatic aberration is unavoidable for electron lenses, and the symmetry is also very constrained and limited. So, if you look at the consequence of all of these problems, you are severely limiting the resolution of the electron microscope, whereas if you look at the Rayleigh criteria and look at the wavelength of the electron microscopes, you should push it to reach a really high resolution. So, if you look at the impact of the aberrations on imaging, in optical microscopy the aberrations blur, but it can be corrected. In TEM, the aberrations affect the phase of the electron wave as well, and not just the intensity also. So, the phase shift of electron wave, again going back to what we saw in terms of the aberration function or the wavefront polynomials that we saw, you can write the aberration function which we introduced in high resolution imaging as well in terms of the wavefront polynomials as well. So, if chi g is the aberration function, g being the reciprocal vector and phi being the azimuthal or the deviation from the optical path, you can always visualize this in terms of combination of polynomial functions that we introduced just a while ago. So, W is the wavefront aberration, and in polar coordinates of the reciprocal space, the G here is spatial frequency in the reciprocal space, and phi is the azimuthal angle. So, the aberrations can now be expanded in terms of a polynomial as some kind of a complex number like this. So, the coefficients here and the order of the spatial frequency together can give you the description of the wavefront very similar to what we saw in terms of the Zernike polynomials. So, if you look at it, n is the radial order, m corresponds to the angular symmetry here. This C subscript n and power m is actually the aberration coefficient, and you have two cases. When m is 0, you have rotationally symmetric systems, and when m is not 0, you have anisotropic aberrations. So, what we have done till now is we have seen that aberration is described as a problem where either your light or your electrons, overall your electromagnetic radiation is not coinciding at a single point, and when it is not coinciding, you look at this lack of coincidence in terms of wavefront, and this wavefront aberration can be described in terms of polynomial, and this foundations of this polynomial kind of a description lie in the ideas of this are drawn from Zernike polynomials. So, essentially in any electron microscopes, in electromagnetic lenses or even in optical lenses, you can expand aberrations in terms of some kind of a coefficient, and when I expand this, if I think of now creating an aberration corrector, if there are means by which I can minimize these coefficients, I can minimize the errors in these lenses and thereby have a system where I can correct the aberration. So, how do we correct the aberrations and overcome the Scherzer's theorem? If you look at spherical and chromatic aberration, these are limits for round electromagnetic lenses. You always have them. We just described this a couple of slides ago. So, in rotationally symmetric lenses, you really cannot eliminate it. So, how do you then create an aberration corrector? This is where the breakthrough ideas came in 1964 and 1966. There were concepts introduced that if you can think of developing designs of lenses or deflectors where you can break the rotational symmetry of the electromagnetic lens, that is by not using circular elements or by not using dipoles, which are also used for deflection, but if you use multiple elements or electron mirrors, you can in principle start correcting for aberration of the circular or symmetric electromagnetic lenses. And what you are trying to do is, by using combination of these kind of multiple lenses, we know that a positive spherical and chromatic aberration is introduced in round electromagnetic lenses. So, with the combination of these, if I invert and introduce a negative CS or negative CC, then I would minimize and I stack these lenses one over the other. I can then reduce the CS and CC value. So, this is essentially the concept of an aberration corrector. So, you deliberately introduce controlled or opposite aberrations to cancel the lens defects. So, the corrector is actually placed just after the electromagnetic lens. If you have it just after the condenser system, you call it as the probe corrector. If it is after the objective lens, you call it as the image corrector. Both are reducing the spherical aberration. In the upcoming slides in this lecture also, I am not going to discuss the design and full details of chromatic aberration, but I will stick to spherical aberration only. But the whole idea is you can introduce a negative aberration with multiple or electron mirrors, and with this, and also by breaking the rotational symmetry, you are introducing a negative CS or negative CC and minimizing the lens defect. So, the key idea is it is not really changing the paraxial rays, it only modifies the higher order ray deviations, and you can achieve this with a series of either hexapole or quadrupole and octupole lens combinations. So, for this kind of an idea and the concept, this is considered as a major breakthrough, and these scientists in particular, Max Heider, Harald Rose, Knut Urban and Andre Krivanek, they were actually awarded and recognized with this contribution with the Kavli Science in 2020, and this has really accelerated the field of electron microscope like anything. I think the first successful demonstration of this happened in the year 1997, and from then on the barrier of electron microscope has been broken, and it is really pushed to look at some amazing things and understand materials in a much better way. So, with this background and with these ideas, let us try to understand how the construction of multipole correctors actually look like. So, as I mentioned, there are two designs. The hexapole design was kind of introduced and demonstrated by these three people from the group in Jülich, and from Andre Krivanek's group, they were more or less working on the quadrupole and octupole combinations, and the hexapole combination was first tried for image correction, primarily tried on the objective lens, and the quadrupole octupole combination was tried for both CS plus CC kind of correction, and in correcting the microscope which is operated primarily in STEM mode. So, this is more like the ideas for probe corrector or STEM imaging is what Krivanek's team was actually mastering. So, with all of these, thanks to them, we now have superb microscopes which are kind of a treat or a dream to work with. So, if you look at the ideas of the concepts of these aberration correctors, if you look at the basic building blocks, you want to break the symmetry, and how do you do this? You have multipoles. So, these are either quadrupoles or hexapoles or octupoles. Mainly the quadrupoles are used for focusing or defocusing and also for chromatic correction. The hexapoles are primarily for correcting spherical aberration, and octupoles are for correcting higher order aberrations, also CS plus astigmatism. The round lenses are still not completely avoided, you actually need them. In fact, what the round lenses actually do is, so when you call them as telescopic systems, you stack these multipoles and round lenses one over the other, and the idea is this introduces a magnification of -1, and it is more or less used to transfer the image from the objective lens through the hexapole to the next hexapole again, and then it is reversed back with the second hexapole. So, it is kind of a transfer lens, and then there are the symmetry planes that you have. These are actually used for cancelling unwanted aberrations. So, this is essentially the idea. If I describe how the aberration corrector works, in fact, I have taken this from one of the papers from Harald Rose. The aberration correctors in electron microscopes are designed as telescopic multipole systems that image one multipole onto another with a magnification of -1, and this arrangement ensures that lower order distortions are introduced and cancelled by the other. So, the way the aberration corrector works is, you intentionally introduce an aberration in a particular direction, and you then introduce the next aberration to cancel out this. So, effectively you are compensating for the lens defects, and collectively the combination of these hexapoles together gives you a CS which is having a negative value, and you are minimizing the CS or CC. So, if you look at the diagram of how the hexapole corrector looks like, So this was first developed by Rosa Haider at CEOS, and it was demonstrated at Knut Urban's lab in Forschungszentrum Jülich. It was on a Philips CM20 microscope with a field emitter, and the construction or the ray diagram of the corrector looks like this. You have a magnetic objective lens, and then you have a transfer doublet. There is a hexapole, the first hexapole, which actually introduces distortion or a third order astigmatism in one direction, and then the next transfer doublet, which transfers this image to the second hexapole. So this is how the hexapole actually looks like, and you are breaking the symmetry of the round lenses with this, and physically this is how the hexapole actually looks like. So the arrangement is, the hexapole 1 is at the front focal plane of this one, and hexapole 2 is at the back focal plane, and thereby through the transfer doublet you introduce a distortion and then you reverse it back. So that is what is happening. So if I look at the correction principle, the first hexapole actually introduces second order distortions and third order aberrations. The transfer doublet images the first hexapole onto the second one with a magnification of -1, and the second hexapole cancels all the second order aberrations and leaves only third order spherical aberration, and this spherical aberration now has a negative value. So the net effect is it produces a negative spherical aberration, and with the modern day correctors and with the advances in the electronics that you have, you can fine tune this so perfectly that you can almost have CS 0, but intentionally we introduce some CS to get improved contrast. There is a lot happening in this area and there is enough published literature on this. So the function of a hexapole correction system is to intentionally distort. Through the transfer lens you have a negative magnification, and with the second hexapole, so the double hexapole combination modifies the wavefront somewhat like this. And if you look at it, if you look at how the faceplate or the diffractogram looks like in the correction software, you are introducing a threefold astigmatism, a second order aberration, or then with the second hexapole a negative spherical aberration. Effectively a combination of these now cancels out the positive CS of the round electromagnetic lens. So this is the hexapole corrector, and likewise you also have the quadrupole octupole corrector. So you have two quadrupole sextuplets, which is 6 quadrupoles each, and totally you have over 12 quadrupoles, and then there are 3 octupoles. The construction looks somewhat like this. So the idea here is you have two symmetric halves, so the upper half here and the lower half here, and you have the quadruple triplets here and the central octupole, and you are kind of imaging these at the coma free plane. And if I look at the working principle of this, the double symmetry that you have, which was shown here, it kind of cancels out coma, distortions and the twofold aberrations, and when you excite these through an antisymmetric excitation, you ensure that you are cancelling out the unwanted effects of the multipoles. And the advantage of this kind of a construction is, by having the quadrupoles here in the lower half as well, you can apply some kind of potential also to not just correct for spherical aberration but also for chromatic aberration. So the combination of quadruple octupole corrector is, you create a distortion, and through this symmetric design you are again correcting for the distortion, and you get sort of negative CS again here, and this cancels out the positive CS of the objective lens. So This is how the idea of an aberration corrector is and the functioning of an aberration corrector is, and we will see how this is now implemented. So, if you replace one of the quadrupoles with some kind of crossed electric and magnetic quadrupoles, this behaves as something called as a first order Wien filter. I will not go into complete description of how this works and how it introduces correction of chromatic aberration in this particular lecture, but what happens is when you have electrons which are propagating with different energies and different wavelengths and velocities, when you intentionally introduce a small electric field and a combination of magnetic field in the quadrupole, you can ensure that the electron that is propagating through this part is undergoing some kind of a deviation, and there is a lateral force due to the potential you apply with these electric elements, and then the fast moving electrons, they would actually bend inward, and the slower electrons would kind of bend slightly outward, and this kind of compensates for the chromatic spread. So, in comparison with the hexapole design, the quadrupole octopole design actually gives you the flexibility of introducing electric elements as well, and that is how chromatic aberration corrector also functions. And modern day microscopes and the correctors use a combination of all these hexapole, quadrupole and octopole elements, and there are very few chromatic aberration corrected microscopes that are installed globally now, but the principle of how this is done is essentially like this, and these ideas are implemented in the neon microscopes. Neon is actually created from Nicholas Delby and Andrei Krivanek, and it is now taken over by Bruker, but they produce mainly STEM systems which are giving you exceptional spectral resolution and also spatial resolution and analytical tools. These are perhaps one of the most stable systems which are operated even at 100, 110 kV, and the construction of neon microscopes is also very interesting. It has a field emission gun on the bottom and the electrons are projected upwards. So, this is sort of counterintuitive to the other designs that are there for commercially available microscopes, but if somebody is interested, I would highly recommend you go read this and understand. It is always nice to think of multiple alternative ways, and it only advances the field and it makes it more and more exciting. So, to implement all of these, the concepts were all developed in mid 90s and the ideas were there from as early as mid 60s. To achieve this and make it successful, it has taken a large amount of time, and the initial attempts mainly failed due to the misalignments of lenses, the mechanical instabilities, magnetic noise, drift and vibrations. And when you now have feedback systems and computer control and you have programs that are correcting and compensating for the aberrations immediately, it becomes more and more successful. And I will show you an example of how the aberrations are measured. In fact, following this theoretical discussion on aberration, there will be subsequent lectures on demonstration of how the aberration corrector functions. We will spend more time on how the image corrector actually looks like, and then I will also show how the probe corrector looks like. And because of the stable electronics and the advances in software and programming, we are now fairly successful in not worrying much about aberrations of electron lenses. So, if you look at how the aberrations are measured, the main technique is there is something called as the Zemlin tableau. So if I have a specimen like this with the deflection coils that I have, whether I am illuminating in a parallel beam mode and operating in TEM mode, or whether I am operating in STEM mode, with the deflection coils I can actually introduce a small deviation in angle. Typically this ranges from small deviations to start with 8 or 15 milliradians for fast correction and 23 or 25 milliradians for the standard corrections, and then you have approximately even 40 milliradian on the new microscopes now to improve the aberration significantly. So if you are operating it for an image corrector, the procedure is you go to an amorphous area within a sample and you obtain the diffractograms, you bring the specimen to the right focus, and then you intentionally change the height slightly such that you get enough of these thorn rings, and slightly off the focus, that is approximately around 200 nanometer defocus, you tilt the electron beam and you are kind of pivoting and scanning around. So you are not just tilting, but you are also rotating, and you obtain the diffractograms at various angles, that is to cover the entire three-dimensional space in front of the optical path of the objective lens. This idea of tilting and obtaining the diffractograms is actually called as the Zemlin tableau, and then you compare these images and then you go back to the polynomial function of aberration and you try to make them as symmetric as possible. The images on the left here are with aberration. You can actually look at these and identify which kind of an aberration is it. I will show them in the upcoming slides. And when it is symmetric and nearly circular, you are free from aberrations. When you operate the microscope without a corrector and you are trying to obtain high resolution imaging in conventional TEMs, you compensate for the distortions in the diffractogram by using stigmation coils and you correct them. But here the idea is slightly more elaborate, and with various combinations of these multiple elements, you compensate for the distortions in the field and you achieve sort of a negative CS kind of a situation. So the most important techniques are you get the Zemlin tableau and the phase correlation methods. You actually extract aberrations from the image series. In particular, when you are looking at STEM, you are forming a probe and you are imaging initially how the probe shape is changing with these tilts as well, and of course beam tilt methods and measuring how much the image shift is there. So with the angle that you are applying, you are looking at the alpha component of the wave aberration function, and with the image shifts you are also measuring the R component, and together you are kind of compensating, and this whole process is automated, and that is what you actually do in corrected systems. I will now show you an example from one of our microscopes. I will show you how the initial distortions look like for a probe corrector, and then how the software generally looks like and how the correction is done. This forms like a foundation to understand the demonstration sessions that follow slightly better. So if you look at this particular screenshot, how do you implement these correctors in the microscope and how do you run the program? Thankfully, the modern day correctors and the software is very good that things are automated. In fact, it's sometimes turning out that you need not be very good with microscope hands on. The automation is so good these days that Just with click of a few buttons, things are happening. But that being said, unless you understand what is changing when you are clicking the buttons, it doesn't help. So what you see here is a ronchogram from I think an amorphous carbon film. I think this is from a gold sample, a standard cross grating sample, and if you see here, there is this kind of a shape, and depending on how large aberration free area you have here, you can compensate for two-fold astigmatism with coarse correction coils, and you can compensate for coma with the beam tilt or pivot points that you actually have in the microscopes depending on the manufacturer you are using. And after you correct for simple distortions like two-fold astigmatism and coma, what you can do is you can start the software, and the concept in STEM probe correction is you obtain an image from an area and you actually get an image of the probe. This is now showing you a distorted probe, and each of these coefficients actually mean something. C1, A1 means you are having the defocus and two-fold astigmatism here, and by clicking these, you actually get a table where if the software now gives you some kind of inputs depending on what kind of a range the measured coefficients are, whether they are within an acceptable range or whether they actually need to be corrected. And as you can see here, all the coils of the corrector and the lens currents are given, and by simply starting the program and following the automation procedure, you can start correcting for the aberrations. And when I click these, I can choose systematically step by step. Typically you start with correcting for defocus and two-fold astigmatism, then B2 or coma, and then you start correcting for A3, S3 and so on, the third order aberrations, and finally you also correct for CS, and it all happens in a sequence. So once you start correcting, and also the first step is start with compensating for focus, whether it is for image correction or for probe correction, and then you start with a tableau with a small angle. You have different modes. When you click this tableau, you have either fast or standard or enhanced, and with a fast scan you then see how the aberrations are, you coarsely correct them, and iteratively you start correcting them step by step. So following the procedures that are given and the standard protocol that you actually have, if you look at how the aberrations are corrected, here is something that I have taken from one of the workshop slides from CEO's website. If you look at how it is for TEM versus STEM, this is the Gaussian image, and here is how the probe looks like in under focus and over focus. It is nearly circular, and this is a state where the probe is well corrected, but whereas these distortions in the probe are not good enough, and you can see the effects of these in the image as well. And if I look at the diffractogram in TEM, you would see there are different kinds of errors, and in fact this should also be read. This is while correcting and this is after correction. You are applying a tilt and you are getting the Zemlin tableau, and if you recollect the Zernike polynomials and the polynomial expansion of aberration, with changing the angle and by measuring how much my image shifts are, and by cross correlation methods, you can minimize the coefficients and then you start correcting the aberrations. So this image I have taken from Martin Link's slide from CEO's website only. This gives you a nice visualization of how different aberrations look like. If I draw an equivalent of this with optical systems, this is like a projection of the wave front that you see, and these shapes you can describe with the Zernike polynomials. So, if you look at the Zernike polynomials and the coefficients that you have there, the TEM notation is you give them these coefficients and they mean something. So, C1 means defocus, A1 is astigmatism, B2 is coma, A2 is threefold astigmatism, C3 is spherical aberration, A3 is fourfold, and B4 is higher coma, and C5 is fifth order. These days, the new frontier is more or less trying to achieve corrections for even sixth order aberrations, but the earlier generations were correcting only up to CS or third order aberrations and also fourfold astigmatism. But nowadays you can also correct up to fifth order or even sixth order aberrations as well. So, how do these aberrations actually look like is this. So, with C1, B2, S3, D4, R5 or A1, A2, these are the TEM notations of these different kinds of aberrations, and by applying suitable compensatory currents through the aberration corrector construction that we saw, you can compensate for the wave front and then you actually start correcting. So, to summarize and to bring back to the first slide that I showed, aberration correction in electron microscopy is actually wave front engineering, and if you draw parallels between optical microscopy and electron microscopy, the foundation is in the wavefront polynomial description, and we also drew a parallel with Zernike polynomials, Zernike circular polynomials, and with combinations of various coefficients of these methodology of representing aberrations as a summation of these circular polynomials, you can describe any kind of a shape of a wavefront. And in electromagnetic lenses, the biggest challenge has been with the circular symmetry of round lenses, and also lenses only being sort of converging lenses. You only have, or for round electromagnetic lenses, you always have a positive CS and a CC value. The breakthrough idea came in with breaking the symmetry of circular lenses by using multipole systems, and with kind of the telescopic mounting kind of principle, that is, you stack one lens on top of the other. The engineering of aberration correctors was done, and with this breakthrough you can actually compensate for the field distortions, or you can compensate for the wavefront distortions through an automated process through a feedback loop, and then achieve resolutions as good as 0.5 angstrom. And in fact, there is a push to even achieve 30 or 0.3 angstroms, 30 picometer and so on. So, with this I would like to end this discussion on the theoretical understanding or the construction and the concepts of aberration correction, and following this there will be 2 demonstration lectures starting with the aberration correction of an image corrector. You will see the layout of how the microscope looks like and how the aberration correction is done, and following that there will be another lecture on spherical aberration correction for a probe corrector. And with this I end this lecture here. Thank you.